Beneath the stars, beyond the galaxies, and in the quiet spaces between atoms, there lies a hidden world, a reality that exists beyond our perception, where the very fabric of space and time is not what it seems. We often imagine the universe as a vast, incomprehensible expanse, governed by predictable laws, where matter and energy interact within well-defined boundaries. But what if this is not the true nature of reality? What if the universe itself is an illusion, a projection of something far deeper, far more complex than we have ever imagined? A place where the very laws of physics bend, warp, and break, where time stretches and contracts like an elastic fabric, and where gravity, the force that holds our world together, can be both a thread that weaves the cosmos and a force that tears it apart. What lies beneath this fabric of reality? To understand the universe, we must look beyond what we can see with our eyes, past the stars, past the galaxies, and into the very core of existence. This journey takes us into the realm of quantum physics, black holes, gravitational waves, and the elusive forces that govern the cosmos. It takes us to the edge of time itself, where the universe bends and twists in ways that challenge the very nature of existence. This is the story of what lies beneath the fabric of reality, a story that begins with a simple question. How do we truly understand the universe we live in when its deepest mysteries lie hidden in the spaces we cannot yet reach? The beginning of space and time. The universe as we know it began with a question that would change everything. Before the 20th century, time was regarded as something fixed, unchanging, a river that flowed in one direction, steady and unyielding. Similarly, space was understood to be a three-dimensional stage, a vast but unbending container where objects existed, interacted, and moved. It was a world we could understand, a world where the laws of motion were simple, predictable, and eternal. But then came the revelation that shattered everything we knew about the fabric of existence. Albert Einstein's theory of relativity. In 1905, Einstein proposed that time was not absolute. It was relative. The flow of time could slow down or speed up depending on how fast an object was moving. It was a profound insight, one that suggested that time, far from being a constant, was a malleable, fluid force, bending and stretching depending on the motion of objects in space. But Einstein's discoveries didn't stop there. In 1915, he introduced the theory of general relativity, which took his ideas about time and space even further. Space and time, he proposed, were not two separate entities, but one interconnected continuum, space-time. Imagine the fabric of space stretched out like a sheet, and massive objects, like planets and stars, causing the fabric to bend under their weight. This bending was not just the warping of space, it was the warping of time itself. The presence of mass affected the very flow of time, slowing it down near massive objects and speeding it up in areas where there was less gravitational influence. This was the first glimpse of what lay beneath the surface of reality, the realization that time and space were not fixed, but were inextricably linked, shaped by the very forces that governed the universe. The implications of this idea were vast and far-reaching. For centuries, we had thought of space as a rigid, unchanging backdrop for the events of the universe. Time, too, had been seen as a simple, ticking clock, universal and uniform. But now, the very fabric of the universe was revealed to be a living, breathing entity, one that could stretch, compress, and bend depending on the forces at play. And then came the experiments, the first tests of these groundbreaking ideas. In 1919, British astronomer Arthur Eddington led an expedition to observe a total solar eclipse. As the moon passed in front of the sun, Eddington noticed something extraordinary. Starlight, which should have passed straight through space, was bent as it came close to the sun. This bending of light was the first direct observation confirming Einstein's theory of general relativity. It was as if space itself had been distorted, causing the light to take a curved path. For the first time, the universe was revealed not as a static backdrop, but as a dynamic, elastic fabric, shaped by mass and energy. But the true scale of this realization would not come until much later, when scientists would begin to understand the more bizarre aspects of Einstein's vision. How gravity could warp time itself, how massive objects could create ripples in the fabric of space-time, and how these ripples could travel across the cosmos. Time, once thought of as a constant, could now be slowed, stretched, and even torn apart. It is in these revelations, in this discovery of the malleability of space and time, that the true nature of reality began to emerge. For centuries, we had walked through the universe blind to the forces at work beneath the surface. But now, we were beginning to see the deeper structure of existence itself. And the more we looked, the more we realized that what lay beneath the fabric of reality was far stranger than anything we had ever imagined. The quantum realm, the hidden world of particles. In the vastness of the universe, where galaxies swirl and stars burn with the brilliance of creation, there exists another realm invisible to the naked eye. A world so small, so strange, that it defies all our intuitions. This is the quantum realm, where particles behave in ways that no classical physics could ever predict. It is a realm where certainty is an illusion, where the laws of the universe seem to bend and break, and where time and space become fluid, subject to forces beyond our comprehension. To understand what lies beneath the fabric of reality, we must journey into this hidden world, a world governed not by the smooth, predictable motions of planets and stars, but by probabilities, uncertainties, and the strange behavior of subatomic particles. In the quantum realm, nothing is fixed, and everything is subject to change. This is a world where particles can exist in multiple places at once, where they can seemingly travel through time, and where the very act of observing something can change its outcome. The birth of quantum mechanics in the early 20th century marked a revolutionary moment in our understanding of the universe. Prior to this, we had a picture of the world built on classical physics, where objects could be measured and their behaviors predicted with precision. But in 1900, Max Planck introduced a concept that would change everything. The idea that energy is not continuous, but comes in discrete packets, or quanta. This idea led to the development of quantum mechanics, a new branch of physics that would reveal a hidden layer of reality, a world of particles that existed not in fixed states, but in a state of constant possibility. One of the most mind-bending aspects of quantum mechanics is quantum superposition. In the classical world, we are used to thinking of objects in definite states. An object is either here or there, moving or stationary. But in the quantum world, things are different. Particles, such as electrons, do not exist in one definite state until they are measured. Instead, they exist in a superposition of all possible states at once. A particle can be in multiple places, moving in multiple directions, and even spinning in multiple orientations simultaneously. It is only when we observe or measure the particle that it chooses a particular state, collapsing its wave of possibilities into a single reality. This strange phenomenon was famously illustrated by Schrödinger's cat, a thought experiment in which a cat inside a box is both alive and dead at the same time, until the box is opened and the cat's state is observed. The very act of observation causes the quantum superposition to collapse into a single reality. This raises profound questions. What happens to reality when we are not looking at it? And how do the principles that govern the quantum world relate to the macroscopic world we experience? The most famous and puzzling of all quantum effects is quantum entanglement. This phenomenon occurs when two particles become so deeply connected that the state of one particle can instantly affect the state of another, no matter how far apart they are. This spooky action at a distance, as Einstein called it, seems to violate the fundamental principles of space and time, which tell us that information cannot travel faster than the speed of light. And yet, experiments have shown that entangled particles can influence one another instantaneously, even across vast distances. Entanglement has been experimentally verified and is now a cornerstone of quantum mechanics. But it also raises questions about the nature of reality itself. How can particles be connected in this way? What does it mean for our understanding of time and space if information can travel faster than light? And what does it say about the very nature of the universe? That distant parts of reality could be so profoundly interconnected, even when separated by vast distances. To answer these questions, we must delve deeper into the quantum world, where the very foundations of time and space begin to blur. Quantum mechanics shows us that the universe is not a collection of separate, individual objects, but a vast, interconnected web of probabilities and possibilities. The fabric of reality is not as rigid as we once thought. Instead, it is woven from threads of uncertainty, tension, and entanglement. One of the most astonishing implications of quantum mechanics is that time itself, in the quantum realm, is not as we perceive it. In the classical world, time flows steadily, a river from past to present to future. But in quantum mechanics, time behaves in strange and unpredictable ways. Time dilation, a concept rooted in Einstein's theory of relativity, occurs not just for large objects moving at high speeds, but also for particles at the quantum level. Time itself becomes fluid, stretched and compressed in the presence of energy and matter. Moreover, quantum tunneling, where particles can seemingly pass through barriers that should be impenetrable, suggests that our understanding of cause and effect is far more malleable than we once believed. The rigid flow of time, so central to our experience, may not apply at the quantum level, where particles leap through space and time, defying classical constraints. And so, as we peer deeper into the quantum realm, we are forced to confront a paradox. The world we experience, with its clear boundaries and predictable laws, is built on a foundation of uncertainty and possibility. The very fabric of reality, the threads that bind space and time together, are woven from the strange and mysterious forces of the quantum world. Time is no longer a fixed backdrop to the events of the universe, but a fluid and dynamic force, shaped by the particles and energy that permeate it. The quantum realm, with its strange superpositions, entanglements, and uncertainties, shows us that the universe is far stranger than we could have ever imagined. The deeper we look, the more we realize that reality is not as it seems, that beneath the surface of space and time lies a hidden world, where particles dance in waves of possibility, and where time and space themselves are mere projections of deeper, more fundamental forces. And, As we continue to explore this hidden world, one question remains. What does this quantum reality say about the universe as a whole? If reality is built on such a mysterious and uncertain foundation, what does it mean for our understanding of the cosmos? What lies beneath the fabric of reality itself, and how can we unlock its deepest secrets? The curvature of space-time, gravity's hidden hand. As we've seen, the quantum realm challenges everything we think we know about the universe. But there is another force, just as fundamental, that governs the cosmos, the force of gravity. Unlike the strange particles and waves of the quantum world, gravity is something we experience every day. It is the force that keeps us tethered to Earth, the force that holds the planets in orbit, the force that shapes the very structure of the universe itself. Yet, gravity, too, hides secrets beneath its surface. Einstein's general theory of relativity, proposed in 1915, revealed the true nature of gravity, not as a force that pulls objects together, but as a curvature of space-time itself. To understand this, imagine space-time as a stretched rubber sheet. When you place a massive object, like a planet or star, onto this sheet, it causes the sheet to bend. The greater the mass, the more pronounced the curvature. In this analogy, the curvature of space-time is what we experience as gravity. Objects do not fall toward one another because of an invisible force, but because space-time itself is warped by the presence of mass. This was a revolutionary idea. Gravity, as Einstein proposed, was not a simple force but a manifestation of the geometry of space-time itself. Massive objects like the Earth or the Sun create indentations in space-time that affect the motion of other objects. When the Earth orbits the Sun, it is not simply being pulled by the Sun's gravity. It is moving along the curved fabric of space-time, following the natural paths, called geodesics, created by the Sun's mass. This understanding of gravity has profound implications, not just for how objects move, but for how we perceive the very fabric of the universe. If space-time can bend and stretch under the influence of mass and energy, then time itself must be flexible, bending and warping in the presence of gravitational forces. This was demonstrated in a number of experiments, most notably in 1919, when astronomer Arthur Eddington confirmed Einstein's prediction that light from stars would be bent by the Sun's gravitational field during a total solar eclipse. This phenomenon, known as gravitational lensing, showed that not only space but light itself could be affected by the curvature of space-time. But the implications of this discovery were even more profound. If space-time could bend under the influence of gravity, then what happens near the most extreme sources of gravity, like black holes? What happens when space and time are so warped that they collapse in on themselves? The answer to these questions lies at the very heart of black holes, regions of space-time where gravity is so intense that not even light can escape. A black hole is the ultimate expression of gravity's ability to bend space-time, pulling everything, including time itself, into an inescapable singularity. At the center of a black hole lies the event horizon, a boundary beyond which nothing can escape, not even light. Anything that crosses the event horizon is trapped, pulled into the singularity, where space-time itself collapses to an infinite density. Time, as we experience it, behaves very differently near the event horizon. To an outside observer, time seems to slow down as an object approaches the event horizon, appearing to freeze just as it crosses the threshold. For the object itself, time passes normally, but it can never return from the black hole's grasp. This stretching and warping of time near black holes is known as gravitational time dilation, and it's one of the most mind-bending consequences of general relativity. In fact, the closer an object is to a massive body, whether it's a planet, a star, or a black hole, the more pronounced the effects of time dilation become. A clock near the event horizon of a black hole would tick far slower than a clock on Earth. This effect has been confirmed experimentally, as atomic clocks placed at different altitudes on Earth tick at different rates. The higher the clock is from the Earth's surface, where gravity is weaker, the faster it ticks. At a black hole's event horizon, the difference would be extreme, showing just how dramatically gravity can affect time itself. But black holes are not just fascinating because of the way they distort time and space. They also offer us a glimpse into the deepest mysteries of the universe. Mysteries that go beyond the observable and into the heart of quantum mechanics. According to current theories, at the center of every black hole lies a singularity, a point where the curvature of space-time becomes infinite, and the laws of physics as we know them cease to function. The singularity represents the ultimate breakdown of reality, a place where the forces of gravity overwhelm the fabric of space-time, and time itself ceases to have any meaning. This concept, though fascinating, also presents a paradox. If time cannot exist in the singularity, then how can we measure the passage of time in such an extreme environment? How can we reconcile the behavior of gravity in these regions with the strange and unpredictable behavior of particles in the quantum world? Here, we encounter the limits of our understanding. While general relativity works incredibly well in describing large-scale phenomena like the movement of planets, stars, and galaxies, it fails to explain what happens at the quantum level, where the laws of physics are radically different. This is the great challenge facing modern physics: how to reconcile the two fundamental theories that describe the universe: general relativity, which governs the large-scale behavior of gravity, and quantum mechanics, which governs the small-scale behavior of particles. In fact, quantum gravity, the quest for a unified theory that can explain both gravity and quantum mechanics, is one of the biggest unsolved problems in physics today. The reconciliation of these two frameworks could unlock the deepest mysteries of the universe, from the nature of black holes to the birth of the universe itself. As we continue to explore the extremes of gravity and the nature of space-time, we come closer to answering some of the most profound questions about the universe. What happens when space and time bend to their breaking points? Can the fabric of reality itself be torn or stretched beyond recognition? And, most tantalizing of all, can we find a way to bridge the gap between the large-scale forces of gravity and the strange, unpredictable realm of quantum mechanics? The discovery of gravitational waves in 2015, for instance, provided the first direct evidence of ripples in space-time caused by the collision of two black holes. These waves, detected by the LIGO observatory, confirmed that space-time itself could be disturbed by the most extreme events in the cosmos. As we study these waves and their effects, we inch closer to a deeper understanding of how gravity works at the quantum level and what it can reveal about the very fabric of reality. The curvature of space-time is not just a fascinating aspect of general relativity. It is a gateway to understanding the most profound mysteries of existence. As we continue to study black holes, gravitational waves, and the fabric of spacetime itself, we come closer to understanding what lies at the heart of the universe. Time and space are not just the stage on which cosmic events unfold, They are the very forces that shape the universe, driving its evolution and revealing its deepest secrets. The hidden dimensions, beyond our perception. As we venture deeper into the fabric of reality, the nature of space and time begins to reveal itself in even stranger and more complex forms. The three dimensions of space and one of time, our everyday understanding of the universe, may not be the only dimensions that exist. For over a century, scientists have speculated that there may be more to reality than the four dimensions we experience. Hidden dimensions, imperceptible to our senses, could be influencing the behavior of the cosmos in profound and unexpected ways. The first inklings of these hidden dimensions came in the early 20th century, with the development of string theory. In the standard model of particle physics, particles like electrons and quarks are seen as the fundamental building blocks of matter, point-like objects with no internal structure. But in the mid-20th century, theoretical physicists began to explore the idea that these particles might not be point-like at all. Instead, they might be tiny, vibrating strings, too small to detect directly, whose vibrations give rise to the particles we observe. These strings could be vibrating in multiple dimensions, far beyond the three we know. String theory proposes that the universe is made up of additional spatial dimensions, beyond the three that we experience every day. According to this theory, there could be up to 9 spatial dimensions in total, in addition to the dimension of time, making a total of 10 or 11 dimensions in the universe. These additional dimensions are thought to be curled up or compactified at incredibly small scales, so small that they are imperceptible to us. The extra dimensions, hidden from our senses, could be influencing the forces and particles we observe in the universe, shaping everything from gravity to electromagnetism. To imagine these extra dimensions, we must think beyond the 3 dimensions of space we are familiar with. Picture a tiny, curled-up circle, too small to see. This could represent a dimension that is curled up at every point in space. In the microscopic world, these extra dimensions could have profound effects on the behavior of particles and the forces that govern them. In fact, string theory suggests that the fundamental particles we observe in the universe are actually the different vibrational states of these tiny, vibrating strings. The way these strings vibrate determines the mass, charge, and other properties of particles, and the extra dimensions determine how these strings vibrate. But what does this mean for our understanding of reality? If extra dimensions exist, how can we detect them? The very idea that space could have more than 3 dimensions seems impossible to grasp, as it challenges our everyday experience. But there is one area where these extra dimensions may reveal their influence: gravity. Gravity, as we know it, is a force that acts on massive objects, pulling them toward one another. In string theory, gravity is explained not by a force, but by the exchange of gravitons, particles that mediate the gravitational force. These gravitons, according to string theory, may interact with the extra dimensions, causing gravity to behave differently than the other forces. Gravity, it turns out, may be leaking into these hidden dimensions, which could explain why it is so much weaker than the other fundamental forces. The fact that gravity is weaker than the electromagnetic, strong, and weak nuclear forces has been one of the great mysteries of physics. If gravity is truly as fundamental as the other forces, why does it seem so much weaker in our everyday experience? One possibility is that the gravity is spread out across multiple dimensions, with much of its influence hidden from our senses. This leakage into extra dimensions could explain why gravity appears weaker in our three-dimensional world, even though it is just as powerful in the higher dimensional space. The idea of hidden dimensions has also sparked new thinking about the Big Bang and the origin of the universe. If extra dimensions existed at the time of the Big Bang, they could have played a crucial role in shaping the universe's evolution. The rapid expansion of the early universe, known as cosmic inflation, may have been influenced by these extra dimensions, which could have caused space itself to stretch at an unimaginable rate. This sudden inflation of the universe could have set the stage for the creation of the stars, galaxies, and cosmic structures we observe today. Yet, despite the elegance and promise of string theory, these extra dimensions remain elusive. Scientists have yet to directly detect them, and much of the theory remains speculative. The energy scales required to observe these dimensions are so high that they are beyond the reach of current experiments. However, there are signs that we may soon be able to probe the existence of these hidden dimensions through experiments in particle accelerators, such as the Large Hadron Collider LHC. As we push the boundaries of particle physics, we may one day uncover evidence that extra dimensions are not just theoretical constructs, but real features of the universe. Even if we cannot directly observe these dimensions, their influence may still be detectable. For instance, the behavior of gravity near black holes or the study of cosmic inflation could offer indirect evidence of hidden dimensions. In addition, new theories in quantum gravity, which seeks to combine general relativity with quantum mechanics, may reveal deeper insights into the nature of space and time, providing a framework in which extra dimensions can be understood. But the question remains: if extra dimensions exist, what lies beyond them? What does it mean for our understanding of the universe if there are dimensions that we cannot even perceive, that lie beyond the limits of our experience? Could there be even more dimensions beyond those predicted by string theory waiting to be discovered? And if these hidden dimensions influence the forces of the universe, how might they shape the future of cosmology, physics, and our understanding of reality itself? The discovery of extra dimensions would not just be a scientific breakthrough, it would be a philosophical revelation. It would force us to reconsider our place in the universe, our understanding of space, time, and reality. If the universe is indeed a multidimensional structure, what does that say about the limits of human perception? How far can we push the boundaries of knowledge before we encounter the ultimate mysteries, realms of existence that exist beyond the dimensions we know? The search for hidden dimensions is more than just a quest for answers. It is a journey into the unknown, where the fabric of reality itself may reveal secrets far beyond our current understanding. As we continue to explore the cosmos and push the limits of our scientific tools, we may one day uncover the true nature of reality, one that lies beneath the surface, hidden in the unseen dimensions that shape the universe. The quantum gravity paradox, bridging the worlds of the large and small. As we've explored the wonders of hidden dimensions, the nature of time, and the curvature of space-time, we arrive at an inevitable crossroads in our understanding of reality. The fabric of space and time, we now know, is not the simple stage we once thought it to be. It is a dynamic, malleable structure, influenced by mass, energy, and even the unseen forces of dark energy and quantum fluctuations. And yet, despite all our progress, there remains a fundamental mystery that has yet to be solved, a paradox that stands at the intersection of the largest and smallest scales of the universe. This is the quantum gravity paradox, a riddle that challenges both our deepest understandings of the cosmos and our most well-tested theories of physics. On the one hand, we have general relativity, Einstein's revolutionary theory that governs the behavior of massive objects, planets, stars, and galaxies, and describes the curvature of spacetime itself. On the other hand, we have quantum mechanics, the theory that governs the behavior of subatomic particles, where uncertainty, probability, and wave-particle duality reign supreme. These two theories have proven remarkably successful in their respective domains. General relativity has allowed us to understand the motion of planets, the behavior of black holes, and the dynamics of the universe on the largest scales. Quantum mechanics, meanwhile, has explained the fundamental behavior of matter at the smallest scales, from the particles that make up atoms to the strange phenomena observed in the quantum realm, such as superposition and entanglement. But when it comes to the most extreme environments in the universe, places like black holes, the Big Bang, or the edges of the Great Void, these two theories cannot be reconciled. In these regions, both the effects of gravity and quantum phenomena are at play, but no theory currently exists to unite them. And as we reach for a deeper understanding of the universe, this gap between general relativity and quantum mechanics presents an intellectual wall that we cannot yet overcome. At the heart of the quantum gravity paradox is the idea of singularities, points in space and time where gravitational forces become infinite and space-time itself breaks down. These singularities exist at the center of black holes, where the curvature of space-time becomes so extreme that the laws of physics cease to function as we know them. At this point, gravity overwhelms all other forces, causing matter and energy to collapse into an infinitely dense point, a singularity, where time and space lose their meaning. In theory, general relativity describes these singularities as regions of infinite density, where gravity is so strong that nothing can escape, not even light. But quantum mechanics tells us something very different. According to quantum theory, the laws of physics cannot function under these extreme conditions. At the quantum level, particles are governed by uncertainty and probability, not determinism. Quantum mechanics predicts that at such small scales, the very fabric of spacetime itself should be subject to quantum fluctuations, meaning that spacetime is not a smooth, continuous fabric, but is instead grainy and subject to small, unpredictable changes. The paradox arises when we try to reconcile these two descriptions. General relativity suggests that spacetime is smooth and continuous, bending under the influence of mass and energy. Quantum mechanics, however, tells us that at the smallest scales, spacetime should be subject to quantum fluctuations, creating a chaotic, unpredictable environment. How can spacetime be both smooth and continuous, as described by relativity, and granular, fluctuating, and uncertain, as described by quantum mechanics? The tension between these two theories has led to the search for a theory of quantum gravity, a framework that can unite the principles of quantum mechanics with the curvature of spacetime. Scientists have proposed several different approaches to solving this paradox, but none have yet succeeded in providing a complete, unified theory. One of the most promising candidates for this theory is string theory, which we touched on earlier. String theory proposes that the fundamental building blocks of the universe are not particles, as quantum mechanics suggests, but tiny, vibrating strings. These strings can vibrate in multiple dimensions, and their interactions produce the particles and forces we observe in the universe. If string theory is correct, it could provide the long-sought unification of quantum mechanics and general relativity, allowing us to understand the quantum nature of gravity. However, string theory is still highly speculative and has not yet been experimentally verified. One of the challenges is that the energy scales required to test string theory are far beyond the reach of current experiments. To detect the effects of extra dimensions or the vibrations of strings would require particle accelerators, with energies many orders of magnitude greater than higher than anything we currently possess. But the possibility that such a theory could provide a unified description of reality remains tantalizing, offering the hope of a comprehensive framework that can explain both the large-scale structure of the universe and the strange probabilistic behavior of subatomic particles. Another approach to resolving the quantum gravity paradox is loop quantum gravity, a theory that suggests that spacetime itself is not continuous, as general relativity suggests, but is made up of discrete, indivisible units, like tiny loops or atoms of spacetime. These loops are thought to be incredibly small, on the order of the Planck scale, and they could explain the quantum behavior of gravity at very small scales. If loop quantum gravity is correct, it could provide a way to merge the principles of general relativity with quantum mechanics, offering a new understanding of the structure of spacetime itself. Despite these efforts, the quantum gravity paradox remains one of the most profound mysteries in modern physics. It is a paradox that reaches to the very limits of our understanding of the universe, one that challenges the foundations of both quantum mechanics and general relativity. And yet, this paradox also represents an opportunity to deepen our understanding of the universe, to unlock the secrets of black holes, the Big Bang, and the very nature of time and space. As we continue to probe the extremes of gravity and the quantum realm, we may one day find the theory that unites these two frameworks. And in doing so, we may gain access to a deeper layer of reality, one that reveals not only the nature of the universe, but the ultimate nature of existence itself. Could we one day discover the quantum structure of space-time? Will we unlock the mysteries of the black hole singularity and discover what lies beyond the event horizon? And if we do, what does that mean for our understanding of the universe's past, present, and future? In this search for quantum gravity, we are not just searching for a unified theory of physics. We are searching for the deepest truths about the fabric of reality. And in this search, we may find that the greatest mystery of all lies in understanding the very structure of space and time, in exploring the hidden layers of the cosmos that have remained concealed for so long. The singularity paradox, at the heart of a black hole. At the center of every black hole lies the singularity, the ultimate enigma of the cosmos. It is a place where space and time collapse into an infinitesimal point of infinite density, where the laws of physics as we know them cease to function, and where the very fabric of reality itself seems to unravel. The singularity is the ultimate expression of gravity's power, a place where matter and energy are crushed to their most extreme, where time itself may stop, and where all our understanding of the universe is pushed to its limits. But what exactly happens at the singularity? What does it mean for the universe when a region of space-time becomes so warped that the usual rules of physics break down? How can a singularity, a point of infinite density, exist in a universe that is otherwise governed by the predictable laws of relativity and quantum mechanics? To understand the singularity, we must first understand how black holes themselves form. Black holes are born when massive stars collapse under their own gravity at the end of their lives. As the star runs out of fuel, it can no longer support its own weight and its core contracts. If the star is massive enough, the core will continue to collapse until it becomes a singularity, a point in space where all the mass of the star is concentrated in a single, infinitely dense point. The result is a region of space-time where the curvature becomes infinite, so extreme that not even light can escape. The boundary surrounding this singularity is called the event horizon. Once an object crosses the event horizon, it is irretrievably drawn toward the singularity. Nothing, no matter, no energy, and not even light, can escape the black hole's grasp. The idea of a singularity is a difficult concept to grasp, especially when we consider that it represents a breakdown in our understanding of physics. Under normal conditions, the laws of physics govern everything from the motion of planets to the behavior of subatomic particles. But near a black hole's singularity, these laws no longer seem to apply. The equations of general relativity predict infinite curvature, where spacetime itself stretches and warps to an unimaginable degree. But as we venture into the realm of the singularity, these predictions become meaningless. The force of gravity is so intense, the density so extreme, that time itself may cease to flow in any recognizable form. At the singularity, all known physical quantities, density, temperature, pressure, become infinite. The fabric of spacetime itself collapses under the immense gravity, creating a region where the usual concepts of space and time no longer make sense. It is, in essence, the point where the universe's most fundamental laws break down. But why does this happen? Why, in the presence of such intense gravity, do the laws of physics cease to function? The answer to this question may lie at the intersection of general relativity and quantum mechanics. General relativity, which describes gravity and the curvature of spacetime on large scales, works extremely well in predicting the behavior of massive objects like planets, stars, and black holes. However, it breaks down at the quantum level, where the behavior of particles is governed by uncertainty, probability, and the strange laws of quantum mechanics. When we try to describe the singularity in terms of general relativity, we encounter a problem. The equations predict a breakdown of spacetime itself, a region where gravity becomes infinite and the fabric of reality collapses. This paradox, the quantum gravity paradox, arises when we attempt to reconcile the principles of quantum mechanics with the intense gravitational forces predicted by general relativity. In the quantum world, particles are not deterministic but probabilistic. They can exist in multiple states at once, and their behavior is governed by uncertainty. But when we attempt to apply this probabilistic nature to the singularity, we face a deep contradiction. The singularity represents a point of infinite density, where gravity is so intense that quantum effects should dominate. But at the same time, the singularity represents a breakdown of spacetime itself, where the usual principles of both quantum mechanics and general relativity no longer hold. This is where the quantum gravity paradox becomes apparent. How can we describe a region where both the effects of gravity and quantum mechanics are in play, but the laws governing both are incompatible? How do we reconcile the smooth, predictable curvature of spacetime described by general relativity with the unpredictable, probabilistic nature of quantum particles? This is the problem at the heart of the singularity, and it is the problem that has stymied physicists for decades. While the singularity itself may remain beyond our direct observation, hidden within the event horizon of black holes, scientists are still pushing the boundaries of our understanding in the hopes of unraveling its mysteries. Some theories suggest that the singularity may not be a point of infinite density at all, but rather a quantum object, with quantum fluctuations giving rise to the seemingly infinite curvature of spacetime. This theory, known as loop quantum gravity, proposes that spacetime is not a continuous fabric, but rather a discrete structure, made up of tiny loops or grains. If this theory is correct, it could provide a way to reconcile the paradox at the heart of black holes and offer a glimpse into the true nature of the singularity. Other theories, such as string theory, propose that the singularity could be the result of higher dimensional objects, such as tiny, vibrating strings, that behave in ways we cannot yet fully comprehend. String theory suggests that the universe is not just made up of particles, but of one-dimensional strings, which vibrate at different frequencies to create the particles and forces we observe. In this framework, the singularity may not be a true point of infinite density, but rather a manifestation of the interaction between the hidden dimensions of the universe and the forces of gravity. Yet, despite these promising theories, we are still far from fully understanding the singularity. Its mysteries remain hidden beyond the reach of our current knowledge and technology. But even as we grapple with these paradoxes, we are reminded of the true nature of the universe. The singularity represents not just a breakdown of physics, but a reminder that the universe is far stranger, far more complex than we can ever fully understand. It is a glimpse into a deeper reality, a world where time and space break down, where gravity overwhelms all other forces, and where the very fabric of existence is stretched to its limits. As we continue to explore the cosmos and seek the answers to these profound questions, we are left with one undeniable truth. The singularity, like the universe itself, remains an enigma. It is a point where our understanding of the cosmos reaches its limit, where the laws of physics dissolve, and where the mysteries of time, space, and gravity converge into one inescapable truth. The universe is far more complex than we ever imagined. And within this complexity, the singularity remains one of its most profound and elusive mysteries. The infinite universe, what lies beyond the observable. As we peer into the depths of space, our gaze is limited by the very nature of our universe. We observe the stars, galaxies, and nebulae scattered across the vast expanse, mapping out the cosmic structures that fill our observable universe. Yet, even as we look deeper into the cosmos, there remains a part of the universe that lies beyond our reach, a portion of space so far away that its light has yet to reach us. This boundary, known as the observable universe, is the limit of what we can detect with our current technology. But beyond this boundary, what lies hidden? What does the universe look like beyond the reach of our telescopes and instruments? The concept of the observable universe is grounded in the finite speed of light. When we observe distant objects, we are looking back in time, as the light that reaches us has traveled across vast distances, often taking millions or even billions of years to arrive. The farther away an object is, the further back in time we are seeing it. This creates a window into the past, a snapshot of the universe as it was when the light we observe was emitted. But the farther we look, the more limited our view becomes. The universe is expanding, and some galaxies are receding from us faster than the speed of light due to the influence of dark energy. This means that the light from those galaxies will never reach us, no matter how much time passes. This expansion is driven by dark energy, a mysterious force that accounts for the acceleration of the universe's growth. But even as we look into the distant reaches of space, we are reminded that the observable universe is only a tiny fraction of the entire cosmos. Beyond the furthest galaxies we can see, there lies an infinite expanse, expanding at a rate that takes it beyond our reach. This area, beyond the observable universe, is not just empty space. It is a region that may contain galaxies, stars, and cosmic structures that we will never see, no matter how advanced our technology becomes. The realization that the universe extends beyond the observable is both humbling and awe-inspiring. It forces us to confront the fact that we may never fully comprehend the vastness of space. We are but a small, finite part of a much larger cosmos, and the universe may stretch infinitely beyond what we can detect. The observable universe is simply the portion of reality we can perceive, and beyond that, there are realms we cannot access, no matter how far we look. This concept, while deeply unsettling, also brings with it a sense of wonder, a reminder that the universe is far grander than we can ever imagine. But the idea of an infinite universe is not just a philosophical notion. It has profound implications for our understanding of reality. If the universe is truly infinite, if it stretches far beyond our observational limits, then what does this mean for the laws of physics? Are the laws that govern the universe, gravity, electromagnetism, quantum mechanics, constant across the entire cosmos, or do they vary from place to place? Could there be regions of the universe where the forces we know behave differently, where the fabric of space-time is warped in ways we cannot predict? And if the universe is infinite, does it imply the existence of an infinite number of possibilities, an infinite number of parallel realities, alternate timelines, or even alternate universes? One possibility that has emerged from the study of cosmology is the idea of the multiverse. The multiverse theory suggests that our universe is just one of many, possibly an infinite number, each with its own set of physical laws and constants. These universes could be entirely different from our own, with completely different forms of matter, energy, and even dimensions. Some versions of the multiverse theory suggest that these universes are not just separate from one another, but that they might interact, influencing each other in ways we cannot yet observe. The concept of the multiverse is often tied to the idea of cosmic inflation, the theory that the early universe underwent a period of rapid expansion, growing exponentially in a fraction of a second. According to some models of inflation, this expansion could have created multiple, separate bubbles of space, each with its own distinct laws of physics. Each bubble could represent a different universe, existing independently of the others but emerging from the same underlying mechanism. If the multiverse theory is correct, then the Great Void, those vast regions of space with seemingly nothing inside them, might not be empty at all. They could be the boundaries between different universes, regions where the laws of physics do not apply in the same way, or even regions where different universes overlap. The Great Void could be a window into a reality far beyond our own, a glimpse into a deeper layer of existence that transcends the limitations of our observable universe. However, the multiverse theory remains speculative, with no direct evidence to support its claims. It challenges the very foundations of scientific inquiry, as it suggests that there may be regions of reality that are fundamentally beyond our ability to test or observe. But this does not diminish the allure of the idea. The notion that our universe is just one of many, that there could be countless other realities existing in parallel with our own, is both humbling and awe-inspiring. It opens up a new frontier in the search for understanding, one that forces us to reconsider what we know about existence itself. The idea of an infinite, ever-expanding universe also raises profound questions about the future of the cosmos. If the universe continues to expand, driven by dark energy, what will it look like in the distant future? As galaxies drift further apart, the universe will become increasingly isolated. The stars will burn out, the galaxies will fade, and eventually, the universe will be left in a state of cold, empty darkness. This scenario, known as the heat death of the universe, is one possible outcome of the universe's expansion. It suggests that, in the far future, the universe will become so diffuse that no significant interactions will occur. There will be no more stars, no more galaxies, and no more life. The cosmos will become an infinite expanse of cold, dark nothingness. But even in this bleak future, the infinite nature of the universe suggests that something new might emerge. As the universe continues to evolve, new forms of matter and energy may arise, driven by the mysterious forces we have yet to fully understand. The Great Void, that vast emptiness at the heart of space, may one day give rise to new galaxies, new stars, and new forms of existence. If not in our universe, then in the countless others that may lie beyond. In the end, the infinite universe and the mysteries beyond the observable are reminders of the limits of our knowledge. As we reach further into the cosmos, we encounter new questions, new paradoxes, and new possibilities. The universe may be vast, unknowable, and infinitely complex, but it is also a place of boundless wonder, where the search for answers can lead us to insights that transcend time and space. The cosmic horizon, the edge of understanding. As we continue our journey through the universe, the concept of the cosmic horizon takes center stage. A boundary not of physical space, but of human comprehension. The cosmic horizon marks the limit of what we can observe, a dividing line between the known and the unknown, the visible and the hidden. Beyond this horizon lies a vast, expanding universe that we can never fully reach or understand. It is the edge of what we can know, a profound reminder that the universe is far grander, far more mysterious than we can ever comprehend. The idea of the cosmic horizon arises from one of the most fundamental characteristics of the universe, its expansion. Since the Big Bang, the universe has been stretching outward, carrying galaxies, stars, and all matter with it. But this expansion is not uniform. As distant galaxies move farther away, the space between them grows, and the light they emit travels ever more slowly toward us. The farther a galaxy is, the faster it recedes from our view. Eventually, there comes a point where galaxies are moving away from us faster than the speed of light, meaning that the light emitted by those galaxies will never reach us. The cosmic horizon represents this boundary, beyond which we will never be able to observe or interact with the universe. This concept is difficult to grasp because we often think of the universe as a vast but fundamentally accessible place. We look at the stars and galaxies, and we assume that if we had the right technology, we could explore them all. But the cosmic horizon reveals a harsh truth. There are parts of the universe that are forever beyond our reach. These distant regions, moving away from us at speeds greater than the speed of light, are forever cut off from our perception. The universe is not only expanding, it is expanding in such a way that the very structure of space itself is taking us farther away from distant galaxies, making them unreachable and invisible. This realization has profound implications. It challenges the idea that the universe is a single, connected whole, accessible to us through the power of science and technology. Instead, the universe is increasingly fragmented, with regions beyond the cosmic horizon forever isolated from us. In the far future, as the universe continues to expand, the night sky will grow darker as galaxies move farther out of view, never to be seen again. The universe will become an increasingly desolate place, its once bright stars fading into the distance, their light stretched and redshifted until it is no longer visible. But the cosmic horizon is not just a limit to our observational reach. It also sets the stage for one of the most profound questions in cosmology. What lies beyond the cosmic horizon? While we can observe the effects of galaxies and other cosmic structures within the observable universe, we are blind to what exists beyond the horizon. Could there be other universes, parallel to our own, with different laws of physics and different forms of matter? Could there be regions of space where time behaves differently, where gravity is weaker or stronger, or where entirely new forms of life exist? Some scientists have proposed the idea that the universe beyond the cosmic horizon may be completely different from what we know. Perhaps the laws of physics are not the same everywhere, and the constants that govern our universe, such as the speed of light, the strength of gravity, and the nature of time, could vary in other parts of the cosmos. This idea is often tied to multiverse theory, the suggestion that our universe is just one of many, each with its own set of physical laws and constants. If this is the case, then the cosmic horizon marks not just the edge of our observable universe, but the boundary between different realms of existence. Universes that are fundamentally disconnected from one another, each with its own unique reality. The multiverse theory is speculative, but it opens up fascinating possibilities. If there are other universes beyond our own, how many are there? Could there be an infinite number of them, each with its own laws of physics, its own history, its own version of reality? And if these universes are beyond the cosmic horizon, can we ever detect them, or are they forever beyond the reach of science? The idea that there could be an infinite number of universes, each with its own rules and characteristics, challenges our understanding of reality itself. What does it mean to be part of a universe if there are an infinite number of others, each with its own version of existence? For now, the cosmic horizon represents the limit of our understanding, a boundary that marks the edge of the observable universe. Beyond this point lies a vast and incomprehensible expanse, a realm where science cannot reach. But while the cosmic horizon may limit our ability to observe the universe, it also sparks the imagination, encouraging us to look beyond the visible and question what lies beyond the edge of our knowledge. The concept of the cosmic horizon and the mysteries it presents challenges us to reconsider the nature of reality itself. It forces us to ask, how much of the universe will we ever truly understand? And what does it mean for the future of humanity when the limits of knowledge expand ever outward, beyond the reach of our instruments and our theories? But there is still hope. The future of cosmology lies in our ability to probe deeper, to extend our reach beyond the cosmic horizon in new and innovative ways. New technologies, such as more advanced space telescopes and observational methods, may one day allow us to study regions of the universe that are currently unreachable. And perhaps, in the distant future, humanity will find ways to transcend the limitations of the cosmic horizon itself, allowing us to explore realms that are, for now, beyond our grasp. The cosmic horizon, in all its finality, is not just an end, but an invitation. An invitation to look beyond what we know, to dream of the possibilities that lie beyond the limits of our current understanding. It serves as a reminder that there is always more to discover, more to explore, and more to learn. And perhaps, one day, we will uncover the true nature of the universe, not by looking at what is visible, but by reaching into the unknown, beyond the edge of the observable, to what lies beyond the cosmic horizon. The end of time, the fate of the universe. As we reach the final chapters of our journey through the fabric of reality, we are confronted by a question both humbling and terrifying. What is the fate of the universe? The universe, it seems, is a place constantly in flux, a realm of perpetual change, driven by forces both known and unknown. From the birth of stars to the collapse of black holes, everything in the cosmos moves through cycles of creation and destruction. But what happens when these cycles come to an end? What will the universe look like in the distant future, when the stars have burned out and the galaxies have drifted too far apart to ever see one another again? At the heart of this question lies the idea of cosmic entropy, the tendency of systems to evolve toward a state of maximum disorder, where energy is evenly distributed, and no useful work can be done. In the context of the universe, this means that over time, the cosmos will eventually reach a state of heat death, a condition in which all matter and energy have reached a uniform temperature, and no further thermodynamic work is possible. The stars will burn out, the galaxies will drift apart, and the universe will become a cold, dark place where life, as we know it, cannot survive. The idea of heat death is rooted in the second law of thermodynamics, which states that the total entropy of an isolated system can only increase over time. As the universe expands, matter and energy become more spread out, and the universe moves toward a state of greater disorder. In the far future, after the last stars have burned out and the last black holes have evaporated through Hawking radiation, the universe will be left in a state of near-perfect equilibrium. Without the energy necessary to sustain processes like star formation, life, or even the basic interactions of matter, the universe will enter an era of deep, unyielding silence. But the heat death scenario is not the only possibility for the universe's future. Another, more catastrophic outcome is known as the Big Rip. In this scenario, the force of dark energy, the mysterious force driving the accelerated expansion of the universe, continues to grow stronger. If dark energy's influence increases over time, it could eventually tear apart galaxies, stars, planets, and even atoms themselves. In the Big Rip, the universe would be pulled apart at an ever-accelerating rate, leading to a violent end where all matter is torn asunder, and time itself might cease to function in any recognizable way. The Big Rip is a more dramatic, more violent end to the universe's story, but it too arises from the mysterious nature of dark energy. If the current rate of expansion continues, the universe could be stretched to the point where the very fabric of space-time breaks down. Gravity, the force that binds galaxies and stars together, would be overcome by the expansion of space itself, causing everything to be torn apart. The galaxies would be ripped from one another, stars would disintegrate, and the very atoms that make up the matter of the universe would be torn apart at the quantum level. In this scenario, the universe would end in a final, violent rupture, a cosmic disintegration that would leave behind nothing but an empty, dark void. Yet another possibility for the universe's fate lies in the idea of the Big Crunch, a scenario in which the expansion of the universe eventually slows and reverses. Instead of continuing to expand indefinitely, gravity would eventually overcome the force of dark energy, causing the universe to contract. Over billions of years, galaxies would fall toward one another, stars would collide, and all matter would be drawn into a single point of infinite density, a singularity. The universe would collapse in on itself, ending in a state similar to the conditions of the Big Bang, a cosmic rebirth, where the universe would start again, cycling through an endless series of expansions and contractions. But even the Big Crunch presents its own set of uncertainties. While it is a possibility based on current cosmological models, the exact nature of dark energy, and whether it will continue to drive the expansion of the universe, remains unknown. It is possible that the universe will expand forever, or it could collapse into a singularity, or it may do something entirely unexpected. The future of the universe remains one of the great unsolved mysteries of cosmology, and every new discovery brings us one step closer to understanding what lies ahead. As we consider these possible futures, the heat death, the Big Rip, the Big Crunch, it becomes clear that the universe is not a static, eternal entity. It is a dynamic, evolving system shaped by the interplay of matter, energy, gravity, and dark energy. The universe began with the Big Bang, a singular event that marked the birth of space, time, and all matter. Since then, it has been expanding, evolving, and undergoing cycles of creation and destruction. But now, as the universe ages, it seems to be heading toward one of these ultimate fates, whether through the slow, inevitable spread of entropy, the violent ripping apart of dark energy, or the crushing collapse of the Big Crunch. Yet, despite these foreboding possibilities, there is something deeply humbling about contemplating the fate of the universe. As we look into the far future, we are reminded that the universe is far greater than we are. Its vastness, its complexity, and its mystery stretch beyond the limits of human imagination. It is a place where time itself flows differently, where the laws of physics are constantly in motion, and where the end of all things may be just as strange and unknowable as their beginning. In contemplating the universe's fate, we are forced to ask more than just questions about the cosmos. We are also forced to ask deeper, more philosophical questions about the nature of existence itself. What does it mean for something to have a beginning, a middle, and an end? What does it mean to be part of a universe that is constantly changing, evolving, and moving toward an uncertain future? And what does it mean for humanity, an infinitesimal speck in the vastness of space, to understand, to explore, and to witness the unfolding of the universe's story? As we peer into the deep future, we are left with a profound sense of awe and wonder. The universe is not just a collection of stars, planets, and galaxies. It is a living, breathing entity, constantly shifting, evolving, and unfolding. The story of the universe, from its beginning in the Big Bang to its ultimate fate, is a story of profound mystery. It is a journey that we are fortunate enough to witness, even if we cannot fully comprehend the depths of what lies ahead. And so, the universe's future, whether it ends in heat death, in a violent rupture, or in a final collapse, is not just a scientific question. It is a reminder that we are part of something far greater, a cosmic journey that began long before we were born and will continue long after we are gone. In the face of the universe's eventual end, we find a sense of humility, a reminder that the universe itself is far beyond our understanding, and its story, its birth, its present, and its future, will always remain a mystery that transcends time itself. The infinite cycle, birth, death, and rebirth of the cosmos. As we stand on the brink of understanding the fate of the universe, we are drawn to an even deeper, more philosophical question. Is the end of the universe truly an end? Or could it merely be the beginning of something new, a cycle that repeats through eons of time? The question of whether the universe is eternal, bound to the infinite cycles of birth, death, and rebirth, has captivated philosophers, cosmologists, and scientists alike for centuries. The idea of a cyclical universe is not new. In ancient philosophies, the concept of eternal return, where the universe undergoes infinite cycles of creation and destruction, was a common belief. In the modern scientific era, this idea has taken on a new form. Cosmological models, built upon our understanding of the universe's expansion, the laws of physics, and the inevitable forces of entropy, suggest that the cosmos may not be a one-time event, but rather a cyclical process, endlessly reborn through a series of phases, each with its own dramatic twists and turns. One of the most intriguing theories about the future of the universe is known as the Big Bounce. This theory proposes that the universe goes through an endless series of expansions and contractions, each cycle beginning with a big bang and ending with a big crunch. In this scenario, the universe would expand from a singularity, reach a point of maximum expansion, and then collapse back into a singularity again, only to repeat the process in an infinite loop. The Big Bounce suggests that the universe is part of an ongoing cycle, where the forces of gravity and dark energy cause it to expand, collapse, and then start again. The theory of the Big Bounce offers a striking contrast to the more conventional models of the universe's end, such as heat death or the Big Rip. Rather than the universe fading into nothingness, the Big Bounce proposes that the cosmos will undergo a series of rebirths, each one marking the beginning of a new cycle. The end of one cycle is not the final end, but a transition into the next. This idea of cosmic rebirth raises fascinating questions about the nature of time itself. If the universe undergoes an infinite series of cycles, each one mirroring the last, what does this mean for our perception of time? In a universe governed by cycles, time would no longer be linear but cyclical. The beginning of the universe would always be the beginning of the next cycle, and the end would always be the prelude to the next beginning. The passage of time would become a loop, a perpetual cycle of creation and destruction. The concept of the Big Bounce also aligns with certain ideas from quantum mechanics, particularly the idea that the universe, at its smallest scales, may behave in ways we can't yet comprehend. In quantum physics, particles can exist in multiple states at once, and reality itself may be a dynamic interplay of possibilities. Could the universe itself be subject to similar quantum principles? Could it be that the apparent death of one universe is merely the quantum leap to the birth of another? This cyclical view of the universe also ties into the idea of eternal recurrence, a philosophical concept that has been explored by figures such as Friedrich Nietzsche. Nietzsche's vision of eternal recurrence suggests that all events in the universe, every thought, action, and experience, will repeat in an infinite loop throughout eternity. In this context, the end of the universe and its subsequent rebirth would be the beginning of the same universe, repeating in an endless cycle. In this way, the universe, rather than being subject to finality, is forever caught in a dance of creation and destruction. As captivating as the idea of a cyclical universe is, it is still a theory that remains unproven. We lack the ability to observe previous cycles of the universe, and much of the evidence for the Big Bounce relies on mathematical models and speculation. But even if the Big Bounce is not the ultimate truth of the universe's fate, it provides an important perspective, a view of the universe as something dynamic, ever-changing, and enduring. It invites us to reconsider the finality of the cosmos, to imagine a universe that is not an isolated, finite entity, but part of an eternal process of creation and destruction. Perhaps this cyclical view of the universe also brings us closer to understanding our place within it. If the universe itself is eternally reborn, what does that mean for the life we experience? If we are part of an infinite cycle, where does our existence fit in? Are our lives just brief flashes within a much larger cosmic narrative, tiny moments in an eternal dance of creation and decay? The Big Bounce, or any theory of cyclical cosmology, ultimately forces us to think about our place in the universe in a more profound way. It forces us to look beyond our own mortality, to see our lives as part of a much larger cycle, a cycle that transcends the boundaries of time and space. If the universe is part of an endless cycle, our lives are not mere fleeting moments, but integral pieces of an eternal process. Each life is a wave in the cosmic ocean, part of a grand, never-ending cycle of birth and rebirth, creation and destruction. But what happens to us as individual beings in such a vast, cyclical universe? If the universe itself is reborn in infinite cycles, what happens to the remnants of each previous cycle? Is the universe truly a new beginning each time, or are the echoes of the past embedded within each new cycle? Could there be remnants of past universes hidden in the fabric of the present one? Traces of lives, worlds, and stars that once existed but are now forgotten? Are we not just observers of the universe's eternal dance, but participants in a cosmic narrative that stretches beyond our individual lifetimes? In the end, the concept of the Big Bounce offers more than just a scientific theory. It offers a philosophical lens through which to view our existence. It challenges us to think beyond the finite nature of our lives, to embrace the possibility that we are part of something much greater, a cosmic cycle that transcends the boundaries of time and space. It invites us to imagine a universe that is not doomed to end, but one that is constantly evolving, expanding, and being reborn. Whether or not the universe follows this cyclical path is a mystery that remains to be solved. But the possibility that the universe is eternal, always reborn, always evolving, is a deeply humbling thought. It reminds us that, in the grand scheme of things, we are all part of a much larger story, a story that stretches through the endless corridors of time, creation, and destruction. And, as we continue to explore the universe, we may one day discover that the end is not the final chapter of this story, but the beginning of something new, something infinitely more profound. The mystery of dark energy, the force accelerating the universe's expansion. As we continue our exploration of the universe's deepest mysteries, we come face to face with one of the most perplexing forces in cosmology: dark energy. It is perhaps the most elusive and enigmatic phenomenon in modern physics, a force that drives the accelerated expansion of the universe, yet remains almost entirely invisible. For all that we know about the cosmos, this mysterious force constitutes around 70% of the universe's total energy content, and yet we know almost nothing about its true nature. Dark energy challenges our understanding of the universe at its most fundamental level. raising profound questions about the fate of the cosmos, the structure of reality, and the very forces that govern space and time. The discovery of dark energy began in 1998, when two independent teams of astronomers observed something that defied expectations. They were studying distant supernovae, the explosive deaths of massive stars, to measure the rate at which the universe was expanding. Based on previous models of cosmic expansion, they expected that the expansion would be slowing down, as the gravitational pull of galaxies and matter would act like a brake on the expansion. Instead, they found something entirely unexpected. The expansion of the universe was not slowing down at all. In fact, it was accelerating. The further galaxies were from us, the faster they were moving away. This discovery sent shockwaves through the scientific community. For nearly a century, the prevailing theory of the universe's expansion was that gravity, over time, would gradually slow the process. Yet here, astronomers were observing the opposite. Something was pushing galaxies apart, something invisible, something that was accelerating the expansion of the universe. They dubbed this mysterious force dark energy. But dark energy is not something we can see, touch, or directly measure. It is not like gravity, which has observable effects on matter, nor is it like light, which can be detected through telescopes. Dark energy does not emit radiation or particles that we can detect. Instead, it is inferred through its effects on the cosmos, the way it influences the expansion of the universe and the behavior of galaxies. In fact, it is the dominant force governing the universe's large-scale structure, shaping its expansion in ways we are only beginning to understand. The most perplexing aspect of dark energy is its repulsive nature. Unlike matter and energy, which attract one another through gravitational forces, dark energy seems to exert a kind of anti-gravity, pushing objects apart instead of pulling them together. The more we learn about dark energy, the more we realize that it is not just an unknown force, but a challenge to the very laws of physics. If matter, energy, and gravity are all subject to well-understood principles, then what exactly is dark energy, and why does it behave so differently from the forces we know? The simplest explanation, according to general relativity, is that dark energy is a property of space itself. As the universe expands, more space is created, and this newly created space is filled with dark energy. The energy density remains constant even as the universe grows, causing the expansion to accelerate over time. This explanation fits well with the idea of vacuum energy, a concept from quantum mechanics, which posits that empty space is not truly empty. Instead, it is filled with quantum fluctuations, brief, spontaneous changes in energy that occur even in the vacuum of space. These fluctuations can have an impact on the curvature of space-time, and might, in some way, account for the effects we observe as dark energy. But even this explanation raises more questions than it answers. If dark energy is truly a property of space, what exactly is it? Is it a new, undiscovered type of energy? Could it be tied to the cosmological constant, a term introduced by Einstein in his equations for general relativity to account for a constant force of repulsion throughout space? Or is it something entirely different, a force that transcends our current understanding of physics? One of the most puzzling aspects of dark energy is its equation of state. The equation of state describes the relationship between pressure and energy density, and it can tell us whether a force, like dark energy, will push galaxies apart or slow down the universe's expansion. Current observations suggest that dark energy has a very specific equation of state, one that leads to the accelerated expansion we observe. But if dark energy behaves in this way now, how did it come to be? Why did it not become dominant until the universe was already billions of years old? And what role does dark energy play in the ultimate fate of the universe? If dark energy continues to drive the expansion of the universe, it could lead to a dramatic and unsettling future. As galaxies move farther and farther apart, the universe will eventually reach a point where stars can no longer form. The supply of gas and dust needed to create new stars will be exhausted, and the remaining stars will burn out, leaving behind black dwarfs, white dwarfs, and neutron stars. The universe will become a dark, cold, lifeless place, devoid of new energy and unable to sustain life as we know it. This future, known as the Big Freeze, is one possible end to the universe. In this scenario, the expansion of the universe will continue indefinitely, driven by dark energy, until everything in the cosmos is stretched so thin that the universe becomes a cold, dark, empty void. But what if dark energy is not constant? What if its effects change over time? Could there be a point where the expansion of the universe accelerates so much that the fabric of space-time itself is torn apart in a big rip? In the Big Rip scenario, dark energy would continue to grow stronger, overpowering even the gravitational forces that bind galaxies, stars, and planets. At some point, the fabric of space-time itself would be torn apart, and the universe would disintegrate, atom by atom. In this violent scenario, everything in the universe, from galaxies to black holes to the very atoms that make up matter, would be pulled apart by the ever-accelerating expansion. These are the stark futures suggested by dark energy, both of which present the ultimate end of the universe. Yet, even as we look toward these possible endings, we are reminded of the fundamental mystery at the heart of dark energy. We do not know what it truly is, why it exists, or how it fits into the larger story of the universe. It is one of the greatest mysteries in modern physics, an invisible force that shapes the future of the cosmos, yet defies all attempts to understand it. The study of dark energy, like the study of the universe itself, is a journey into the unknown. As we probe deeper into the nature of dark energy, we may one day unlock the secrets of the cosmos's most profound forces, gaining a deeper understanding of how the universe began, how it evolves, and how it will eventually end. Dark energy, in its elusive and mysterious nature, may hold the answers to some of the most fundamental questions of existence. And yet, as we stand on the precipice of discovery, we realize that we are still just beginning to understand the very forces that shape the universe. What lies beyond dark energy? What forces drive the expansion of space? And what role does dark energy play in the ultimate fate of the cosmos? The answers, hidden in the deepest recesses of the universe, may one day reveal themselves, changing the course of science and the future of humanity. The final questions: what lies beyond the edge of knowledge? As we conclude our exploration of the universe, the fabric of reality, and the forces that govern existence, we are left with an inevitable question: what lies beyond our understanding? The universe, vast and complex, continues to surprise us with its mysteries. We have come far in our journey to comprehend the forces that shape the cosmos, from the bending of space-time to the strange and elusive dark energy. Yet, even as we unravel the deepest secrets of the universe, we are reminded of the limits of our knowledge. There are questions that remain unanswered, phenomena we have yet to explain, and realities beyond our reach. At the heart of this uncertainty lies the nature of existence itself, the very question of why the universe exists in the first place. For centuries, philosophers and scientists alike have wondered, why is there something rather than nothing? What is the origin of all that exists, and what lies beyond the observable universe? These questions transcend the realm of science and delve into the very essence of existence. They are questions that no equation can answer, no telescope can observe, and no experiment can resolve. They are questions that touch on the most profound aspects of human curiosity. The desire to understand our place in the cosmos, to understand what lies beyond the boundaries of space, time, and knowledge. One of the most enduring mysteries is the origin of the universe itself. The Big Bang theory, which posits that the universe began as a singularity, an infinitely small point of infinite density, has become the dominant explanation for the universe's birth. But the Big Bang raises a fundamental question. What came before the Big Bang? What caused the universe to emerge from this singularity, and what existed before it? In the framework of general relativity, the Big Bang marks the beginning of space and time. But if time itself began with the Big Bang, then what can we say about the nature of before the Big Bang? Was there a before at all? Or is time itself a construct that came into existence with the universe? Some cosmologists propose the idea of a multiverse, suggesting that our universe is just one of many, each with its own set of physical laws and constants. In this model, the Big Bang could be just one event in an infinite series of births and rebirths, a cycle of creation and destruction that spans multiple universes. But even this theory raises new questions. If there are many universes, each with its own laws, how do we account for the constants that govern our own universe? Why do the physical laws in our universe seem so finely tuned for life? Could there be universes with entirely different laws, where life as we know it would be impossible? And if the multiverse exists, how can we ever know if we are truly alone in our universe, or if there are countless other realms out there beyond the edge of our perception? In addition to the mysteries of origin and existence, we are also faced with the question of consciousness, the nature of awareness, thought, and perception. What is consciousness, and how does it arise? From the physical processes of the brain. Is consciousness an emergent property of complex systems, or is it something more fundamental, intrinsic to the fabric of reality itself? Some theories propose that consciousness is a fundamental aspect of the universe, woven into the very structure of space and time. If consciousness is more than just the product of neurons firing in the brain, then could it be that awareness is embedded in the fabric of the cosmos, influencing the way the universe behaves at the quantum level? These questions, though deeply philosophical, are also scientific in their implications. If consciousness is truly a fundamental aspect of reality, it could have profound consequences for our understanding of the universe. It could open up new possibilities for the relationship between mind and matter, and for the nature of reality itself. It could even suggest that the universe is not just a collection of particles and forces, but a living, conscious entity, a universe aware of itself, unfolding in an infinite dance of thought, perception, and creation. As we peer deeper into the mysteries of the universe, we are also confronted with the limits of our understanding. The more we learn, the more we realize how little we truly know. We have uncovered the forces that shape the cosmos, the power of gravity, the strange influence of dark energy, the behavior of particles at the quantum level. But these discoveries only lead to more questions. What lies beyond the cosmic horizon, beyond the limits of our observable universe? What is the true nature of time and space, and how do they relate to the fabric of reality? What happens when we reach the boundaries of knowledge? Are we truly at the end, or are we just beginning to scratch the surface? The universe is a place of infinite complexity, and as we continue to explore it, we are forced to confront the deepest questions of existence. What is the ultimate purpose of the cosmos? Is there a grand design, or is the universe simply a product of chance, governed by the laws of physics and probability? And what is the role of humanity in this vast, unknowable universe? Are we just fleeting observers, watching as the universe unfolds, or do we have a deeper connection to the cosmos, an integral part to play in its unfolding story? These questions, though unanswered, are what drive us to explore, to discover, and to understand. The search for meaning, for truth, for knowledge, is what propels us forward as a species. And though we may never have all the answers, it is this search that gives our lives purpose. It is the desire to understand the universe, to uncover the mysteries that lie beneath the surface of reality, that shapes our quest for knowledge and our understanding of ourselves. As we look out into the stars, beyond the galaxies, beyond the great void, we are reminded that the universe is vast and unknowable, but it is also alive with mystery and possibility. The end of one journey is merely the beginning of another. And as we continue to seek answers to the questions that define our existence, we are forever connected to the infinite cosmos, forever part of the unfolding story of the universe itself.